Well, in the last class we were beginning to learn how to obtain the differential equations from a bond graph, and we learned that we essentially ask two questions. One, we ask about all the elements, what do they give to the system, and we ask to the integrally causal storage elements, what do they receive from the system. So, just by answering these two questions and trying to express the answers in terms of the identified state variables, we get the equations. And we had done it with respect to one system in the last class. Let us recapitulate by working out another example. Let us take a circuit example today. So, in this example, we have a source of effort E, then connected to a resistance, connected to an inductance. Here is another inductance, here is a capacitance, and finally another resistance. Suppose this is my circuit. There will be R1, R2 here, L1, L2 here, and C. Okay. So, when we begin to do the bond graph of this, we start from one of the ends, say the SE element. So, we start from the SE element here. It shares the same flow with R1. So, it will be a one junction connected to an R, which is R1. Then this combine shares the same effort with the L1, right. So, it will be connected to a 0 junction with I, which is L1. It is inertial element which is designated as I. Notice that I am not directly writing L1 here. There is a generic representation of a resistive element as R, inertial element as I. So, we are writing that way. Now, after this stage, it is in series, whatever this combination is, that shares the same flow with L2. So, it will be a one junction connected to I L2, and finally, here these two share the same effort, they have the same voltage. So, it will be a 0, there will be two things connected, one I will connect this side, it is R, which is R2, and here it is C, which is there is only one C, yeah, it is visible. Okay. So, that completes the story. Now, let us put the power directions and the numbers. Now, when we want to put power directions, we start from the AC element, power directed outwards. These ones will have the power directions into the elements, and here, since the power is flowing in this direction, there is only one power source. Therefore, it is logical to put the power directions here like this, though you may choose to do it otherwise, because these are bond to junction bonds. So, let us do it this way. Now, let us give the causalities. How would you assign the causalities? Where would you start? Okay, let us start from the source of effort. The effort is causal in what way? This way. Because it receives the flow information and gives out the effort information. Then this element I, normally what does it do? Okay. In this one, is it completely causal? No, because it has not yet, is a one junction, it has not yet received the flow information. So, only when it does so, we will say that it is completely causal. So, here we will first put this which means that the I element is receiving the effort information and giving out the flow information, and it has come to the 0. It is not yet causal, because 0 will be completely causal if a strong bond brings in what information? Effort information. Okay, so let us move to the next one. Here let us put the moment you do that, the flow information has come into the one junction, and therefore the flow information must go out of the one junction. So, these two are immediately causal. Fine. Come to this point now. See, it has taken out the effort information, it has taken out the effort information, and therefore this bond must bring out the effort information. So, it must be like this. So, here is a one junction which has received the flow information, and therefore the flow information must go out. Okay. Now, you come to the last one, 0, which has received the flow information, but you need a effort information. Normally the C element would create the effort information and bring it here, and therefore the moment you do that, the other ones are immediately causal, because this has brought in the flow effort information, and effort information will go out through these two, which is doing now. Okay. So, all these bonds are now causal. Is that clear? Okay. Now, let us give numbers. Simply 1, 2, 3, 4, 5, 6, 7, 8, and 9. Done. So, we are through. As far as drawing the bond graph is concerned, we are through. Now, the next stage is to obtain the equations. Now, let us ask the first question. So, that is the first question. Let us ask this question to all the elements. Let us start. First, SE, what does it give to the system? SE gives the effort information, which is E1. So, E1, which is, we know, E. Next come to the R1. So, R1. What does it give to the system? R1. Notice here, you have to refer not to this, but to this in order to find out what it gives. It gives effort. Okay. It is not by any means seen a priori unless you draw the bond graph, because a R element could give both the informations. Now, here in this specific case, it is giving out the effort information. So, we start with E2. E2 will be related to its own character, which is, yes, R1 times F2. Then we have to find out where did this F2 information come from. F2 information has come from this as a strong bond. So, this is equal to R1 F3. Now, F3 information, what does it come from? 0. Therefore, F3 is a combination of this and that. And notice the power directions, the F3, because the voltages are equal, efforts are equal. So, F3 is equal to F4 plus F5. Is that right? Because of the power directions, remember that. Had the power directions been opposite, then it would have be, it would be some minuses. So, here it is R1 F4 plus F5. Done. Now, F4 is known. Why? Because it is a state variable. So, we are through. F5, what is it? F5 should be coming from somewhere, and F5 is coming from this bond, F6. So, is R1 F4 plus F6 actually. Now, we can write the things properly. R1 into F4 is what? Actually, while writing this, we should have done it for the storage elements first, because then it would be directly available, but we can see the F4 is P4 by L1. So, it is P4 by L1 plus F6 is P6 by L2. Done. Have you noticed how we went about? We basically try to figure out where does the information get created, and we reach that particular thing. This will always be some storage element, and therefore, ultimately we get the right hand side in terms of the state variables. Fine. Next, we move on to these three. These three would be trivial. For L1, what does it give to the system? Yeah, F4, which is P4 by L1. Then L2, what does it give to the system? F6, F6 P6 by L2. C, what does it give to the system? E8. Can you see that? It gives to the system E8. E8, which is yes, Q8 by C. Okay. So, this is done. Oh, one thing left here. Let us do that. See, is there space? I will push it a little up so that you can see. We can write here. R2, what does it give to the system? F9. So, R2 F9. F9 is E9 by R2. Fine. So, we have related to the character of that particular system element, and then E9 we have to scout the rest of the bond graph to find out where this fellow got created. E9 was created at E8, right. So, E8 by R2, and E8 we know Q8 by 6 is equal to Q8 by R2C. Fine. So, we have obtained everything. We have obtained the answers of this question related to all the elements. So, the first part is done. Second part. The second part, the second question is, what do the integrally causal storage elements receive from the system? Yes, this is important, though in this particular problem all the storage elements are integrally causal. Can you see that? For the I element, an integral causality is where the causal stroke is here, because then it is receiving the effort information and giving out the flow information, and they are integrally related. For this it is correct, for this it is correct, and therefore, all these storage elements are integrally causal. So, our state variables are F4, F6, E8. So, we ask this question with respect to these elements. So, let us start. First, we ask this question with respect to L1. Or basically it is better to write that I am asking the question with respect to I element connected to bond 4. I element connected to bond 4. What is it received from the system? E4. So, we will say it is E4 and E4 is equal to P4 dot, no P4 dot. That is the character of any integral or any inertial element, that the effort is the P4 dot, that is it. So, we bring this thing to this side is equal to E4. So, the dotted term is in the left hand side and the undotted term in the right hand side, and then we try to figure out where this information comes from. E4, E4 where did it come from? It is connected to a 0 junction and therefore, there should be a strong bond bringing in that information, which is E3. So, that is E3. Now, E3, yes, this is one junction and therefore, that is a combination of not E1 plus E2. Notice here the power direction has to be considered. E1 is equal to, note the power direction, is equal to E2 plus E3. And therefore, E3 is E1 minus E2 minus E2. Okay. This is E1 minus E2. Now, both these we already know, E1 we know, E2 we know from the answers to the last question, just substitute. So, we get this as E minus R1 P4 by L1 plus P6 by L2. Fine. So, one differential equation obtained. Second, we ask the question related to the I element connected to bond 6. So, I6. What does it receive from the system? It is E6. So, E6 is equal to P6 dot, and then we bring it to this side E6. Now, E6 is, yeah, this is one junction, therefore, notice E5, the power direction is that way, is equal to E6 plus E7. So, E6 is nothing but E5 minus E7, E5 minus E7. Good. Where does the information E5 come from? E3, yes. So, E3 here, and where does the information E7 come from? E8. So, minus E8. Fine. Now, E3, where does E3 come from? E1 minus E2, yes. So, E1 minus E2 minus E8. Okay. You see E8 minus E3 minus E8, E3 minus E8, E3 has come from E1 minus E2, and E8 is fine, E7 is equal to E8. Okay. Now, all these are known in the right hand side, just substitute, because E1 is known from here, E2 is known from here, and E8 is known from here. Just substitute, you will get it. Happy? Okay, let us go to the C element that is connected to C connected to 8, bond number 8. How will you write it? F8 is what it receives from the system, and that is equal to Q8 dot is equal to Q8 dot, and then bring it to the side is equal to F8, and then find out where the F8 comes from. F8, this is a 0 junction, and therefore it has to be related to F7 and F9. Yeah, F7 minus F9 is equal to F8 because of the power directions. Fine. F7 minus F9. F7 minus F9. F7 comes from F6. That is a strong bond bringing in the information to the one junction when it becomes distributed to the two sides. So, F6 which is known, so we will not bother about that. F9 is also known, minus F9 which is also known. Just substitute. F6 is known because of this, F9 is known because of this, substitute, you will get it. Okay. Yeah.
So there should be E5 plus E7 at the place of for E6.
Where?
F6 should be.
Wait, let us see, let's check. This is okay. E6 is E6 is E5 minus E7, E5 minus E7, and E5 is coming from here.
So why E5 minus
Power directions. Okay. Your question is why is this true? This part E6 is equal to E5 minus E7. Let's illustrate that. In this particular one junction, you have the power direction like this, power direction like that, power direction like this, which means that E5 F5 is going in minus this is going out, E6 F6 this is also going out, minus E7 F7 should be equal to 0 because there is no power here. Now, it is a one junction, which means the effort full flow equalizing junction, which means the flows are all equal, they cancel off, which means we were interested in F6 E6. So, E6 goes this side, which is E5 minus E7, is that right? Okay. So, E5 minus E7 was correct. Fine. Have you understood the procedure? Then all these are known from this. So, you just substitute, you get the equations. Okay, fine. Let us do another problem related to, we have already done the motor problem, right? In the motor problem, your system description was you had a DC motor and it was connected to a source, and there would be the internal resistance, inductance, and this was constant, field was constant. This was connected by means of a shaft to some rotational mass, which is allowed to move against a frictional element. That was the system description. Now, when we obtained the bond graph, how did we go about it? We started from the applied voltage here. So, it would be AC, which is E, that is connected in series with the inductance and the resistance. So, connected with one junction to the I element, which is armature inductance L A, to a R element, which is R A, armature resistance, armature inductance, and that shares yes, that shares the same effort with whatever is here. Now, what is here? It sees the electrical circuit sees it as a something that gives a back EMF, okay, and that we have already seen that that would be represented by a gyrator. So, it is a gyrator here with ratio K phi, and the gyrator will be connected to this side. So, this is the electrical side, this is the mechanical side. The electrical side's effort is the back EMF, and that is related to the speed of rotation in this side, that is the flow. The electrical side's flow is the current, that is related to the torque in the mechanical side, okay, that is why it is a gyrator. Fine. So, we have come to this point. At this point, here is a rotational element which will have its own mass as well as its bearing friction. So, they, whatever the mass is, whatever the bearing friction is, shares the same flow, shares the same flow with this. So, it will be a one junction, it will be a I, which was I 1, and here it was a R 1. So, here it is I 1, here it is I 2. Now, here there was a springiness, there was some bit of freedom, some degree of freedom, so that they can move somewhat independently of each other, that this point and that point share the same effort. Yes, they share the same effort. As a result of which, this C element will be connected by means of a 0 junction to the C, which is K. Okay. Then in this side you have these two elements sharing the same flow. So, it is 1 I 2 R 2. So, that is the bond graph. Let us give numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Now, let us give the power directions. Here these are very standard. So, let us not spend time on explaining these. Now, since there is only one source, it is logical to have the positive power flow assumed to be in this direction, though as I told you, you can as well put them on the opposite direction, but let us do it this way. Now, let us assign the causalities. First, SE element will be receiving the flow information and giving out the effort information. At this point, this one junction is not causal. So, let us put the causality of the I element, integral causality, which is like this. The moment it brings in the flow information, it has to take out the flow information, and therefore, this junction becomes completely causal. Well, the flow information is coming this way into the gyrator, and therefore, the effort information must go out, which means the stroke must be here. Okay. So, here the flow information is coming in gyrator, therefore, it is multiplied, the flow is multiplied with the K phi to give the effort information. So, the information flow would be effort in this direction. So, effort goes out. Now, this one is not yet completely causal, because this is not a strong bond. So, we have to put the causality, integral causality in this storage element, which is like this. The moment you do this, it has already obtained the flow information and must take out the flow information in the other bonds, which is right. Next you come here, this is not yet causal, so let us put it here. This is the integral causality for the C element, and the moment this receives the effort information, it must give out the effort information in the other two bonds like this. One junction, if you put the integral causality like this, it has received the flow information and therefore it must take out the flow information. It is already taking out the flow information here and it must take out the flow information like this. So, this is how you causal it. So, it has been power directed, numbered, causal, done. Now, let us start the business of obtaining the bond graphs. What are the state variables here? Huh? Yes, yeah, F2, F6, E9, F11, right here. Oh, sorry, no, F's are not the wrong. P2, P6, Q9 and P11. These are the state variables. Fine. So, let us start. Ask the question. What was the first question? What do the elements give to the system? Let us ask this question to the first. So, let us start with first one, E1. So, what does it give? It gives E1, E1 is E. So, the first question I answered. Next come here, it gives F2, F2 is P2 by LA. I am just writing with commas so that we conserve space. This one, okay, let us finish the storage element, it will be easier. This is F6, F6 is equal to P6 by I1. This gives E9, E9 is Q9 times K, okay, times K, and your F11 is P11 by I2. So, we have done it for all the storage elements and the source. These were simple, but now let us do it for the 3 resistances. First one, this fellow, what does it give to the system? E3, yes. So, E3 is equal to RAF3 is equal to, now we start to find out where this F3 information comes from. F3 information obviously comes from F2. So, RAF2, which is known RAP2 by LA. So, completed. Second one, what does it give to the system? E7. E7 that is R1 F7, and F7 information comes from clearly from here, that is a strong bond bringing in that information. So, R1 F6, which is again simple, R1 P6 by I1. Similarly, the last one, this one, it gives E12. E12 is equal to R2 F12, and F12 information comes from simply here. So, R2 F11, which is also known R2 P11 by I2. So, all these answers are obtained. We are happy. Have we obtained everything? No, not really, because the gyrator element also gives something to the two sides. Let us take stock of that. What does the gyrator element give to this side, and what does the gyrator element give to this side? Well, to this side it gives, yes, effort, E4. So, to this side it is E4. So, when we start with E4, that is K phi times F5, K phi F5, so yes, F5. F5 comes from F6. F6 is P6 by I1. हो गया. Next, what does it give to this side? It is, what does it give to this side? No. What does it give to this side? No. See, yes, yeah, E5, because it gives E to this side, it gives E to this side. Can you see that? Because the causalities. The way the causal structure is there, it gives E to this side, E to this side. Therefore, E5. E5 is K5 E4. F4. Sorry, F4. Now, F4 information, where does it come from? F2, simple. So, K phi F2 is equal to K phi F2 is P2 by LA. Okay. Had it been a transformer, yes, then it would be different. But since it is a gyrator, it gives, if either it gives flow to both sides or it gives effort to both sides. So, we have done it. Now, let us ask the second question. First, let us ask this question to I in bond 2. I2. What does it receive from the system? I2, it receives effort 2. So, E2 is equal to P2 dot. So, bring it to this side is equal to E2, and then E2, where do you obtain E2 from? Yes, it is a one junction, therefore, E1 minus E3 minus E4 is equal to E2 because of the power directions. Are you now comfortable with how to set the pluses and minuses from the power directions? E1 minus E3 minus E4 is equal to E2. E1 minus E3 minus E4. Okay. E1 is known, is equal to E minus E3. E3 is known. E4 is known, right? All these are known, substitute. Can you see that? E1 is known, E3 is known, E4 is known. Put it. So, you get R A P 2 by L A minus K phi P 6 by I 1. So, that is one differential equation with the dotted term in the left hand side and undotted terms in the right hand side. Now, let us ask this question 2, this one I 6. Here it receives E 6 is equal to P 6 dot is equal to E 6. We will start from here. P 6 or E 6, E 6 where did it come from? Yes, because it is a one junction, it will be effort summing junction, therefore, E 5 minus E 7 minus E 8. E 5 minus E 7 minus E 8. Okay. E 8 is equal to where did this information come from? E 9, because that is a strong bond. So, we can write E 5 minus E 7 minus E 9. Now, you notice that all these are available. E 5 here, E 7 here, E 9 here, just substitute. Okay. So, if you substitute, you obtain K phi P 2 by L A minus R 1 P 6 by I 1 minus K Q 9 dot, sorry, not dot, K Q 9, K Q 9, sorry. So, this is the second. Now, we ask this question in relationship to this one, which is C in the bond 9, C in the bond 9. It receives flow F 9, F 9 is equal to Q 9 dot is equal to F 9, and then we scout the bond graph to find out where does F 9 come from. F 9 is E 8 sorry F 8 minus F 10 in this bond, F 8 minus F 10. F 10 is actually coming from F 11 and F 8 is actually coming from F 6. So, F 6 minus F 11, and both these are available. F 6 is here, F 11 is here, put it in, is equal to P 6 by I 1 minus P 11 by I 2. Done. Finally, let us ask this question in relationship to this one, I connected to bond 11, I 11, it receives effort. So, E 11 is equal to P 11 dot is equal to E 11, we bring it to this side and then find out where does E 11 come from. It is E 9, no, E 10 minus E 12. Okay. E 11 is E 10 minus E 12 because of the power directions, E 10 minus E 12. E 10 is coming from E 9. So, E 9 minus E 12 should be directly available. So, because it is related to this, E 12 is available and E 9 is here, put it in. So, you have E 9 is K Q 9 minus E 12 is R 2 P 11 by I 2. So, these are the 4 equations done. Whenever we ask such questions in exams, and when the result whatever you have obtained are linear, you should always give the final result in terms of a matrix equation. Okay. So, can you express this as a matrix equation? Do that first. Do not give the final answer in exams like this. If the resulting equations are linear equations, always express that as a matrix equation. So, it will be in this case this is P2 dot P6 dot Q9 dot and P11 dot is equal to something times P2, P6, Q9 and P11 and whatever this matrix is. For example, in the first equation it is plus the things that are the external input. So, this will be E, this is related to minus R A by L A minus R A by L A, okay, the first one. Next one is minus K phi by I 1 times P 6 and this is these two are 0 0. Fine. Notice it is in the right hand side you only have P 2 and P 6 and not the other two state variables. So, these two terms will be 0. Next one P 6 dot contains these terms, it contains P 2, P 6 and Q 9. So, P 2, P 6 and Q 9, but not P 11. So, these 3 will be there and then you can write K phi by L A, K phi by L A for P 2 term, P 6 term the second one minus R 1 by I 1 minus R 1 by I 1, third one minus K 0 and so on and so forth. Clear? Make it a habit, whenever the equations are obtained in linear form, always give the final thing in matrix. This will be the vector of state variables, which is say x dot is equal to, this will be called the A matrix A. This is the x vector x plus B u, u is the externally applied force. So, you will always express these equations in this form. Fine. Okay. Now, please complete the rest. That will be trivial, and I am not showing each and every term for it. So far, whenever we were trying to obtain the bond graph, we were following some kind of a logical procedure. In case of electrical circuits, what did we do? We started from say the left side and went on into the circuit, trying to argue which ones share the same flow and which ones share the same effort. For simple circuits, these are fine. I mean, you can argue things, but for more complicated circuits, something that looks like a jumble of things, it will be rather difficult to do it that way. So, there you need some kind of a blind procedure which will work. The blind procedure is something like this. Say if we take this circuit, we had obtained this bond graph by simply working by logic. Now, in this case what we will do, the procedure which is somewhat algorithmic will be that identify the points that can be at different voltages, what are called the nodes. So, what are the nodes here? Here, fine, these are the nodes. So, in this case all these nodes, if they are in different voltages, so things that are connected between them should share the same voltage. Okay. And in so point is that in between these two nodes, whatever are connected, they should share the same voltage, and in between two nodes, if there is a element that shares, the two sides of it share the same flow. So, in between you can connect by a one junction. Let us illustrate. Let me redraw it and then do it, otherwise it will be difficult for you to see. You need to see both the things together in order to appreciate. Okay. Here you have this point, this point, this point and this point at different voltages. Fine. So, you will say that these are simply blindly put at as the 0 junction. So, a 0 here, a 0 here, a 0 here and a 0 here. Okay. Here is the 0 junction, here is the 0 junction, here is the 0 junction and here is the 0 junction. So, there are 4 zeros. Between these two there must be a 1 junction and a resistance connected to it. Between these two there must be a 1 junction with an inductance connected to it. Between these two there should be a 1 junction connecting a C and there will be another 1 junction connecting a R. Fine. Clear. Between this and that you have 1 junction connecting a SE. Have you connected everything? Yes. Huh? One more inductance. Yes, yes, yes. Between these two, between this point and this point. Fine. So, 1 junction connected with the inductance. Okay. We have blindly done it. We have just said that these 4 points represent different voltages. In between whatever are connected by 1 junctions. Done. Okay. But now we have landed up with a bond graph that will turn out to be containing more number of bonds than you really require. For example, this is a 0 junction which is connected to only 2 things. Therefore, the effort whatever comes here must go here, whatever flow here must go here. The powers are equal and the effort and flow are also equal. Therefore, this 0 junction serves no purpose. You can short it. That is one way of shortening the bond graph. The other way of shortening the bond graph is to say that is something that we always do. We say that let this be at the ground potential. So, if that is at the ground potential, how is it reflected here? This is this bond. We will say that here you have connected a SE element which is equal to 0, right. The moment you say that this is equal to 0, this bond carries no power, therefore, it can be ignored. Not only that, it is a 0 junction where the effort is 0, therefore, all these bonds carry no power, therefore, they can be ignored. Have you understood the line of logic? That this we always say that one of the voltage points or nodes would be at 0 potential. There is no harm in doing that. That is a datum, and then the moment you do that in the bond graph, that is reflected as AC becoming 0, and AC becoming 0 connected to 0 junction means all these bonds will carry 0 effort, therefore 0 power, because the power is effort multiplied by the flow. So, all these are unnecessary. Now we see that this again becomes a through junction, is unnecessary, this is also unnecessary, fine. This is also unnecessary, we can connect it, this is also unnecessary, we can connect it. Is there anything else? Okay, this is 0, therefore this has become unnecessary, this can be connected. Now at this stage it looks ugly, so let us just redraw it in a more handsome way. What will you say? AC connected to 1, SE connected to 1, connected to R, connected to 0, 0 is connected to I is connected to 1, the 0 is connected to 1, to I, to a 0, to R and C, that is it, right. And notice that this is exactly the same as what we had earlier. Just check once. By argument we had obtained this, by blind procedure we have obtained this, they are exactly the same. Okay. So, the act of drawing bone graph can also be somewhat algorithmically done. I will illustrate that further in the next class. Thank you.